Hello friends, welcome to Engineering Funda family. In this video, I'll be going to explain you BJT in active region, and this video is very essential in terms of learning concepts based on working of BJT, as well as this video is very essential in terms of questions to be asked in university examination. And in this video, at last, I'll be deriving few essential parameters by which you can solve problems based on BJT in competitive examination as well. So let us try to understand first how we can keep BJT in active region. So here I'll be considering PNP transistor. To keep BJT in active region, emitter based junction that should be there in forward bias and collector based junction that should be there in reverse bias. So that is what I'll be doing by having a battery connection over here. So you see in between emitter and base, I'll be connecting battery as per positive terminal that is connected with emitter and negative terminal is connected with base, that is VBE battery, by which we can keep emitter based junction in forward bias and we need to keep collector based junction in the reverse bias. So to have it, you see here I'm connecting one battery, and to have this junction in reverse bias, this N type is connected with positive terminal and this P type that is connected with negative terminal. That is how we can have this in reverse bias by this battery, that is VCB battery. So once you connect this supply as per this biasing, now this BJT is there in active region. Now as this BJT is there in active region, now I'll be explaining you how current will flows, right? So here, see, let us consider first how externally current will be there. So we are having three terminals. You see, this is emitter, base and collector. So here, see, current will get entered inside emitter. That is what the case which I am considering right now. Let us say here, current is coming out from base, that is IB, and coming out current from collector is IC. So that is how three different colors are there. Let me explain that. See, this is a current. This is a current which is IE, this is a current which is IB, terminal current, right? And this is a current that is IC. So here you can understand one thing. See, this IE current that is entering to this device, this IC current and IB current that is leaving to this transistor. So if you apply KCL, then you can say entering current is equals to leaving current, right? So here let us apply KCL, right, at transistor. So what you will be getting over here? Entering current, that is IE, that is equals to leaving current, that is IC plus IB, right? This is what the basic current equation that you can have. Now our agenda is to understand how internally current will flow. Let me explain you that step by step. So here this is PNP transistor. So obviously this emitter will be having higher doping concentration, collector is having also higher doping concentration, base is having lower doping concentration. So current will flow due to holes over here, right? So if you talk about this biasing, which is VBE, which is given at emitter base junction, so that will inject current over here inside emitter, right? Now here, due to holes, current will flow as majority carriers over here, that is holes. So here if I say current due to holes over here at emitter, so that is IPE. You see, P means holes, E means emitter current. So IPE, that is coming over here at emitter base junction. Now see, this current that is flowing like this, towards collector, right? So here at collector, IPC means current due to holes at collector that is flowing over here. So what will happen? Partial current due to holes that is flowing over here, at base side, and that is happening due to recombination, right? So here there will be recombination, hole current at base side, and that will be how much? IP, this difference, right? IP minus that will be IPE minus IPC. That will be happening due to recombination, right? So let me note it down over here. This IPE minus IPC is due to recombination at base, right? This is happening at base. Now see, this is what about current due to holes, but what will happen due to electrons? So you see this emitter base junction that is there in forward bias. So as this is there in forward bias, motion of electron that will happen from base to emitter, right? Electron will be flowing from base to emitter as this junction is there in forward bias. So current due to electron at emitter, that will be happening in the direction of IPE only. See, this is there in forward bias. So this is there in forward bias. You see, this is there in forward bias. So here, as this is there in forward bias, electron will flow in this direction. And as electron is flowing in this direction, current due to electron at emitter will be there in this direction, right? So here INE that will flow in this direction. That is current due to electron in emitter, right? And here if you talk about this junction, which is collector based junction, so that is there in reverse bias. As this is there in reverse bias, there will be reverse recovery current that will flow, and that will happen due to minority carriers. See here, this is there in reverse bias. So obviously there will be reverse recovery current. So reverse recovery current that will happen at this junction, right? And that will be happening from N to P. Reverse recovery current will happen from N to P, that we have seen it in PN junction. So here, see, you can say here we will be having reverse recovery current, that is ICO, right? And this ICO, let me note it down. This ICO, that is reverse recovery current, right? That is happening due to minority carriers, is due to minority at collector base junction, right? It is happening due to collector base junction. So here minority carriers at N side, that will be holes, and at P side that will be electrons. So you can say this ICO, that will be combination of ICO due to electron and ICO due to holes, right? So you can say ICO, that is NICO plus PICO, right? This ICO, that is reverse recovery current, which will be there due to electrons and holes. So this ICO will be NICO plus PICO, right? But here if you observe, we are having P-type collector and N-type base, and collector is having higher doping concentration compared to base, right? So the value of PICO, that will be higher. Let me note it down so that it will be more clear for you. So this ICO over here, that will be NICO, right? And that will be PCO, right? Minority current due to electron over here and hole over here. So value over here for this PNP will be having due to IPCO. Why? The reason is, here we are having collector. Collector is highly doped compared to base. As collector is heavily doped compared to base, value of IPCO, that is higher, right? So you can say this is higher as collector is doped with higher concentration compared to base, right? So this is what you should know compared to base. The reason is, based on this, there can be question in competitive examination. So see here, how many currents are flowing? First you need to understand that. See here, we are providing emitter based junction, forward bias, collector based junction, reverse bias. This is PNP transistor, so obviously holes are majority carriers. So holes will be flowing like this as per this biasing. So at emitter, holes current will be IPE and partial current will be having recombination at base, and further current will go to collector. So collector current due to holes will be IPC. So recombination current at base will be IPE minus IPC, right? And here, see, as this emitter base junction in forward bias, here emitter current will flow due to electrons in this direction, right? It will flow due to electrons in this direction, and that will be happening due to the majority carriers of base which are electrons, right? So majority carrier of base that will be flowing in this direction. Because of that, INE will flow in this direction. Value of INE that is lower compared to IPE. Why? The reason is emitter is heavily doped compared to base, right? But still at emitter total current is IPE plus INE. Here recombination current at base, that is difference of IPE and IPC. Why? The reason is recombination is happening over here. And as collector base junction is there in reverse bias, here reverse recovery current will flow from N to P, and that is ICO. That ICO will be as per INCO plus IPCO, right? Due to electron and due to hole. But due to hole, current will be higher. Why? The reason is collector is highly doped compared to base. But if you have been given with base is highly doped compared to collector, then you can say this INCO is higher compared to IPCO, right? Sometimes there can be twist. Now what I'm going to do is I'm going to explain you this emitter current, base current and collector current separately as per the explanation which I have given. So let me note down that. So how much emitter current is flowing? IPE plus INE, right? And that is happening due to injection, that you should know, right? So here we are having emitter current first. So how much emitter current that is flowing? Emitter current is IE. So that is IPE plus INE, right? Now if you talk about base current, so base current is flowing due to recombination. So that is IPE minus IPC. So let me note it down. See, base current over here, base current. So that is, let us say IB. So that is IPE minus IPC, right? That is happening due to recombination of holes. And if you talk about collector current, so you see collector current, that is IPC plus ICO. Collector current is IPC plus ICO, you see. So here collector current, if you talk about that, then that is IC. So that is equals to IPC plus ICO. Here, as I have told you, ICO is ICO due to electron, that is INCO, and ICO due to holes, that is IPCO. Here usually IPCO value that is greater compared to INCO, right? That is how things are there. Usually we write it as ICO, that is a combination of these two, right? We don't write this two separately. You will be writing this alone, right? Now see, based on these currents, now I'm going to explain you parameters, right? So let us see how parameters are there. So first parameter that I'm going to explain you, that is injection efficiency, that is also referred as emitter efficiency, and notation is gamma over here. In some books notation may differ, so note down those notations as per explanation given over here. The reason is in future when I solve examples, at that time I'll be using notations as per the notation which I'm using it over here, right? So injection efficiency or emitter efficiency, that is gamma. Let me define it first. So this gamma is injected carrier at junction E, right? See, injected carrier at junction E divided by, injected current at junction E divided by total current injected at emitter. Injected current at junction E, that is IPE, divided by total current is IE, right? So here definition is what? Injection efficiency, that is injection, that is injection current at junction E divided by total current at emitter, right? So injected current at junction E is how much? Here injection of holes is happening, so IPE divided by total current at emitter is IE, which is IPE plus INE, right? So here you can say this injection current at junction E, that is I of PE divided by total current at emitter, that is IE, and this IE is IPE plus INE. That is what I have explained you right now, right? Emitter current, that is this. Now let us have second definition, that is transportation factor beta. So transportation factor beta explains what? How much injection is getting transported at collector. See, transportation factor beta, that explains what? How much injection that is getting transported at collector. So injection at collector divided by injection at emitter, that is transportation factor beta star, right? So let me note down the definition. See, this beta star, that is transportation factor, that is injection at JC, that is injection current at JC divided by injection current at JE. So injection current at JC, that is how much? IPC, and injection current at JE, that is how much? IPE. So this is what? This is what? Transportation factor beta, right? So these are the current which is happening due to holes, as we are talking about PNP BJT, right? Now third is alpha, that is current gain, or you can say that is large signal current gain. See, here there are multiple ways by which you can understand this. First of all, let me give you one basic relation. Alpha is gamma into beta star. Alpha is gamma into beta star. That is one relation that you should know. Here gamma is IPE. You see, gamma is IPE divided by IE. Let me write it as IPE divided by IE, and beta star is IPC divided by IPE. So here you can observe this IPE will get cancelled. So you will be having IPC divided by IE, right? Now what is IPC? So if you observe here, see, IPC is current due to injection of holes in collector, and total collector current is IC, and IC is IPC plus ICO. So IPC, that is IC minus ICO, that you can say. So if you can substitute that, you will be getting, you see, IPC, if you can substitute that, then you will be getting alpha is equals to IC minus ICO divided by IE, and based on that you can say IC is equals to alpha IE plus ICO. So here there are few equations that you will have to understand, and based on that there will be questions in future, right? So I'll be making some videos in which I'll be solving some examples. So alpha is gamma into beta, that relation that you should know. Collector current is alpha times IE plus reverse current, that you can say. You see, alpha explains what? How much transportation is happening over here, plus ICO, right? So alpha into IE plus ICO, that is collector current, right? ICO plus IPC, but IPC is how much? Alpha times of IE, right? That is how one can calculate IC current. Secondly, when you want to calculate gamma, then that is how much injection efficiency is there. So total injection current at emitter divided by total emitter current. So here, see, if injection is higher, then see, IPE divided by total is IPE plus INE. So if INE value is lower, then that injection efficiency will increase. So practically, when we design BJT, at that time we wanted to have lower value of INE, and lower value of INE that you can have based on lower doping concentration in base, right? So one should know, see this relation gamma, that is IP divided by IE, where IE is IP plus INE, where INE value that should be lower. Technically this gamma value that is lower than 1, but it will be nearer to 1 ideally, right? Transportation factor that explains how much injection is reaching to collector. So injection at collector divided by injection at emitter. So IPC by IPE, that is how it is there. So these are the definitions that you'll have to understand and you'll have to remember it. The reason is, in future when you solve problems, at that time that is very essential, right? Still, if anything that you would like to share, please note it down in comment section. I'll be happy to help you. Thank you so much for watching this video.